Hi, welcome back to LeetCode. So, in this video, we discuss LeetCode problem 3624 number of integers with pop count depth equal to k 2. So, the prerequisite for this problem is you should know about segment tree or Fenwick tree. Okay, because this is actually the efficient or optimal data structure to fetch or query any range based count, right? So, what is the problem statement? Problem statement is that you are given an integer array nums for any positive integer x. Define the following sequence. Starting p0 is equal to x. Okay. Next p of I plus 1, it will be pop count of p of I. That means the previous number. For all I greater than 0, where pop count y is the number of set bit 1 in the binary representation of y. That means suppose we actually have 7. So this actually is the p0. So p1 will be what? Pop count of 7. So binary represent, if actually represent this 7 in binary, so what will happen? 4 plus 2 6 and 7, right? So this actually 3 bit actually, this 3 actually set. So p1 will be what? Ultimately 3. Got it. So what will be p2? So if I represent this number 3 in binary, so what will be the number? So this will be 2 plus 1, it is actually 3. So how many actually set bit actually present here? 2. So p2 will be 2. Next p3 will be what? The pop count of 2. So if I represent this 2 in binary, so what is the number will be? So this will be this kind of, right? This is the binary representation of 2. So how many set bit actually present? 1. So we should stop in this when actually we got actually this current number actually as 1. So this sequence will eventually reach the value 1. The pop count depth of x is defined as the smallest integer d greater than or equal to 0 such that p of d is equal to 1. So for this 7, suppose this is the current number. So what is the depth for this? What is the depth, pop count depth for number 7? So it is actually 3, right? Because in the third time, like this is the 0th time, this is first time, this is the second time, this is third time. So in the third time, we actually have the number as 1. So the depth, pop count depth for number 7, it will be actually 3. Got it? Now, for example, if x is equal to 7, so the pop count depth actually it is 3. Clear? So it means in the depth 3, our actually number will be 1. Got it? So now what do they want? They want that you are also given 2D integer array queries. Okay. So you actually have some queries. So for each query is either there are two types of present. This is actually type 1 and this is type 2. Right. So what is the first type? First type is that 1, L, R, K. So what it indicates? So we have to determine the number of indices j such that j is between greater than or equal to L and less than or equal to R, and the pop count depth of nums j is equal to k. So that means we actually have some array, right? Now in this type 1 query, we actually have some range L and R, and we will get some depth. So what is to return? We have to return that how many, like, so suppose this is the L and this is the R. So we have to count that within this range, how many actually number actually pop count depth is equal to depth. Got it? So we have to count that. Clear? Clear the problem statement. And the next type, another type actually possible, it is actually 2 idx value. That means update nums of idx to value new value. Okay. So that means it actually updating the, suppose we actually are trying to update this index with the new value x2, suppose. So that means this is dynamic. So this actually we can't actually store or pre-calculate the value at the beginning. This is not possible because our array can be modified. So again, so So brute force approach will be what? So every time when I actually got a type actually query, so I will iterate the range from L to R, and I will check that for each number what is the depth, right? And I actually increase the count. If the depth of the current number is equal to the depth actually we want, then actually we will increase the count. And ultimately after iterating all the numbers actually present in this range, I will actually store the total count actually I have. Got it? So this is actually brute force approach. So that means suppose there actually q queries actually present, q queries. So it will be possible that every time I am first updating a new number, then actually we are actually calling the L to R range. Got it? So it actually worst case it will be actually for each query I have to iterate L to R, L to R. Alright. So this will q into n. So if the length of the range is n, so it will q into n. So it actually m square. Right? It actually clear. It will give us tailing. Why it will give us tailing? Clear. Now let's see the example one. So then actually we will see that by using a segment tree or Fenwick tree, how we will optimize this. So I think you can relate how actually we can use the Fenwick tree here, because it's a range based query and this is a dynamic array, because in some query we actually update the number and then actually it, like previously it was a 7. Okay, so for this index the pop count depth was suppose x1, then I have modified this with 8, then pop count depth can be changed to x2, right? It can be changed to x2. So if it is changed to x2, then actually it actually the whole range we have actually modified this, because it actually affect all actually the number that you present whenever you will count in the range. So that's why we can actually use Fenwick tree or segment tree to optimize this. Now let's see the example one. So we actually have two numbers, 2 and 4. Okay, first query is type 1, right? This is indicate the type 1 query. So we actually have two range L and R. So L here it is actually 0 and R is actually 1. And what is the depth? Depth actually is 1. So first number actually I have 2. So what is the depth for 2? So first depth is number is 2. So how many actually binary set bit actually present in the binary representation of 2? 1. So D1 will be 1. So our depth for this number 2 is actually 1. Depth is 1. And for 4, what is the depth? So D0 it will actually 4. And D1, what is the how many set bit present in 4? 1 0 0. So that means only one actually set bit actually present. So this is the depth is also 1. Depth of 4 is also 1. Clear? Now I want to know that for this range 0 to 1, how many actually number is present whose depth actually 1. So how many? 2. So that's why our output is first is 2. Got it? Next we actually type 2 query. That means we're actually trying to update a new number. So how actually trying to update index 1, and which number actually I'm trying to replace? It will be replaced with 1. So previously the array was 2 4. Now 4 will be changed to 1, and the depth of 2 it is actually depth was 1, and for 4 it was actually 1, but it will be changed now because I have changed a new number. So depth 0, it is a number is 1, so it is already 1, so here the depth will be 0. Got it? Now what is the next query? Next query is type 1 query. Okay, that means we have to find out how many numbers actually present within this range whose depth actually is the current target. So the range is 0 to 1. Okay, means the whole array, and the here actually the target depth actually 0. So how many actually number actually whose target depth actually 0? Only one number, because one number actually depth is 1, another number depth is 0. So we have to return only 1, because only one number actually depth is 0. So that's why here actually you can see that next output is 1. Clear? How are you getting the output? So I can use the segment tree or Fenwick tree, both actually possible. So how can I optimize this? Because they mention that here actually you can see they mention that k value or the target depth can be only 0 to 5. So 6 different type actually are 6 different depth are possible, right? So in the with the input array, I will check that which now actually depth is 0. Okay, then I will actually create the segment tree. Okay, suppose this is a segment tree one whose number actually is depth is 0. Okay, now another depth, I will create another segment tree whose depth actually is 1. Okay, so actually that means we actually count only the numbers, the actual depth is actually 1. So in this tree it will be counted. Okay, so in this tree I will actually count till 5. Got it? Okay, now what I have to do, this is the initial step. By using the input array, I will actually create 6 different Fenwick tree or segment tree that actually store that actually give us that from L to R. Suppose I actually know that in this tree, I know that in the range base that how many actually number actually present whose depth actually is 0 and range is L to R. Okay, I can easily find out that. Similarly, for actually our target, I know the target depth is actually 1. So from this tree, I will actually check that within this range L to R, how many actually number is still present. I can easily find out that, because first here actually you are getting the map, right? So first map that depth, then for each depth create a segment tree or Fenwick tree, both actually possible. Got it? So mapping is clear. First I will go to the depth or the target depth, then it will check that for this depth, for this range L to R. So that for to get the range based query, I have to use segment tree. So for this, the first key it will be depth. Then it will check that for this L to R, I will, for this particular tree of this particular depth, I will check that for this range how many actually number actually present. Got it? Now next, this is the type 1 query, or actually there is no updation, right? Now there is another query type is present that actually to update any number. So that time I will check that, suppose I know the index, that this index value will be changed to value 2, right? I know the old value also, this is the old value. So from this old value I will check the what is the depth. So, and I know that new depth, this is the new depth, new number. I can easily find out that what is the depth for this current number. So we'll check that if the old depth and the new depth both are different, then what will happen? So it will actually remove from the tree that actually previously it was present. Like previously it was depth was actually suppose 3, suppose. So it will be actually, we have to actually adjust the tree that actually for depth 3, right? So for depth 3 I will actually remove one number, this particular index. Okay, and suppose here actually depth I got actually 2. So for this depth 2 tree I have to add a new number for this particular index. Got it? So what I have to do efficiently, I hope this is clear logic. Now go to actually code. So here actually I have used Fenwick tree. You can actually use the segment tree also, both are actually possible. So first of all, I have to I know that the maximum number of depths possible is 6, like 0 to 5, right? So I have actually taken a variable 6. So I have to know that how many number is present. Okay, and I have to create the Fenwick tree of depth of size like all possible depth 0 to 5. So that's why I have created a vector of Fenwick tree. So 0 index, it indicates the depth 0. What is the tree? Got it? It's indicated that. So I know that the maximum size is possible is 6. So that's why I have initialized with 6. And for each depth, I will check that first of initialize the tree. Okay. So I actually initialize a Fenwick tree of size n, because in worst case it will be possible that all the depth all the number depth is same. So then actually to place only one tree. So that's why, and the tree size it should be n, because n number should be present. The range can be 0 to n minus 1. So that's why I initialized a tree for each depth. Here actually now tree is empty, but I know that in the size will be n. Right? So after this for I have initialized the Fenwick tree. And how many Fenwick tree I have initialized? 6, like for each depth. Got it? Now what I have to do? I have to create the initial Fenwick tree or segment tree by using the initial number. So by input array. So I know that I have to map the depth also. Otherwise, I have to calculate again. You can also skip this. Again, you actually before, like when you're trying to update a new number, so we should know what is the old depth, the depth of the old number. So you can also pre-calculate that, or I can actually store that here actually. Otherwise, you can actually calculate that time also, like when you're trying to update. So here actually I've created new vector to know that what is the depth of the any number or index wise. So n numbers are present. So actually n index are possible. So I'm iterating each number 0 to n minus 1. I'll check that what is the depth of the current number. So I'm passing the current number and I need to return that what is the depth of the current number. So in the current index, I'm storing the depth. Okay. And for this particular depth, you could just see this here. First level key is the depth of the current number. Then for that, so first of all, I map the depth. Then for that particular depth, I know that what is the tree, Fenwick tree, corresponding Fenwick tree. So for the tree, I will actually store the current number index I and increase the value by 1 because it will be counted. It will increase the count by 1, right? For this particular depth. So that's why I'm increasing, I'm actually inserting the particular index I, I'm increasing the value as 1. So after this for loop, I have, by using the input array, I have created the segment tree for particular depth, right? So initially I know that for this particular depth, what is the segment tree, and for the segment tree, I already have the Fenwick array. Or I can easily find out that, or I can easily fetch the value that for this range L to R, what is the number actually present, how many number actually present, whose depth actually current depth. Got it? So now we have to return vector of integer because for each type 1 query, like here actually you can see that like I am returning vector of integer. So the for the type 1 query, I have to return that how many number actually present, who is present in the range L to R, and the depth is also same, the target depth. Got it? So that's why I'm iterating the each queries, and I'll check that this is the type 1 query. Okay, so then what I have to do? I have to fetch the range based query. I will do. So I will get 3 things. One is the left range, left LR, and the K means the target depth. So now I'll check that if K is less than 0 or K greater than equals to 6, so that means this depth is not possible. So I'll store 0. Else I have to fetch that for this particular depth, how much number actually present within this range L to R. So that's why I'll check this for particular depth. First of all, map that particular depth, target depth. So then our query will be what? The range L to R. Got it? How to optimize this here? Otherwise, you can actually iterate from L to R every time and check that what is the for the current number I that actually between L to R. Check what is the depth. If it is equal to the target depth, then actually we will increase the count. So then actually it will be n square. So here actually you can actually using the Fenwick tree so to get this efficiently. So L to R, I am passing the range that for this range L to R, how many actually number actually present. So it will return the count. So store this into the answer. Got it? Now for this else, that means this is a type 2 query. So that means we are trying to update one number. So that means I know the index and the new value we are trying to update. So I'll check that what is the old depth for this particular index and what is the new depth. If it is not same, then we have to update. Otherwise both are actually same, then index is also same and the depth is also same, then it will not affect anything, any other tree also, any other Fenwick tree. So that's why it will only affect if the depth is different, old depth and the current depth. So that time what I have to do, for the old depth I have to decrease one number. So that's why you can see that for the old depth I am decrease the current index with -1. That means we are decreasing because we are removing the current number. Got it? And for the new depth, we are actually inserting this new number for this new depth. So for this particular index, I am increasing +1. Got it? And I am actually to optimally get this what is the depth of the current index or the current number. So to know that, I am just storing the what is the new depth now. Got it? And also in the array nums of index value, modify the new value. Got it? So ultimately return the answer. Now here actually I am using two. One is the Fenwick tree and I actually using the pop count depth. That will return the depth of the any number. So pop count depth, I will get one number x. So what is the depth? Depth will start from 0. So till we have to continue till actually our number is not equal to 1. So actually our number is equal to 1. So we have to break. So till our actually x not equal to 1. So I'll check that how actually this actually function return this is inbuilt library function that will return that for any number how many set byte actually present. So this will return that how many set byte is present. Again I will store the x and I will increase the depth. Got it? And ultimately whenever actually x is equal to 1, so d actually store the depth is starting from 0, so return the d. Got it? Now this Fenwick tree. So Fenwick tree I have initialized with n because n number actually present. Input size actually array size actually n, so our range can be from 0 to n minus 1. So I actually created a new vector here actually inside the Fenwick data structure. So of size n plus 1 initialized with 0. That means there is no 0 means there is no number actually till now initially. Now I'm trying to update index I, and this is actually the basic Fenwick tree algorithm to update, to insert any number or to query any number. So that's why you can just see here that for horizontal trying to insert any number for this particular index I with the current value v. So I'm start from x is equal to I plus 1 and x less than equal to n. I'll continue. And what is the next index? It will be x plus equal to x into x end of minus x, and I will increase the count of that particular index. Got it? So this is to insert any new number. Similarly, for get any index, similar way I have to subtract this because I'm starting from x is equal to I plus 1, okay, and x greater than 0, and then what will next index? Next I have to subtract here because next I actually added next, and before I am trying to insert that from L to R. Fenwick tree means what? 0 to L, 0 to I, any index, 0 to I. So that means I have to continue, start from I, then previous index that is possible. So that's why I'm going to the forward left side. Got it? So x minus equal to x in minus x. So I'm add this current value into the sum variable and ultimately return the s. So that actually return the number actually present between 0 to I. Got it? But what actually I actually want to know from L to R. So that's why I have to write another query that will return from I to J. Got it? From L to R actually. So I'll see that if R less than L, so that means 0. This is not a valid range. Otherwise, how to do? First of all, find out what is the count for 0 to R. Then subtract with 0 to L. Got it? So L minus 1. Then actually it will actually, so that means what is I'm trying to do? So we actually know the, suppose this actually the L to R. Suppose this is actually the L to R. Okay, L to R. And this is 0 and this is n minus 1. Okay. So to know this particular, in Fenwick tree we can only know about 0 to I, right? In Fenwick tree. So here actually I have to know L to R. So what would you do? First of all, find out what is the value for this 0 to R. Okay. Then find another, this actually suppose C1, and find another query to get till this L minus 1. They actually give us this count 2. So what will be actually count for L to R? It will be C1 minus C2. Clear? So here actually I am trying to do that. So first of all, querying this function again, calling this function, horizontal passing R. That means we will get the count that is the number present between depth is same. Depth is actually where this particular tree is for particular depth. So how much number is present from 0 to R? Got it? And then we have to subtract what? From 0 to L minus 1. So I'll check that if L greater than 0, that means we actually have some number. So that time I'll actually store, again I'm calling this query function, passing L minus 1, else it will be 0. Got it? So if I subtract this from query R of L minus 1, I'll get that how much number is present between L to R. Clear? So that actually ultimately we want to know. So we are calling this function actually from the this pop count depth function. Here actually you can see that from this query we are passing two things, L and R. Actually, function overloading is possible. You actually have done that function overloading. Got it? Because a different argument is present L or R. So when you're passing two argument, it will call this function, and it will ultimately return that how many actually number is present between L to R. I hope this is clear. And if you find this video useful, please like the video, and if not subscribe, please subscribe channel. Thank you.